So Constexpr keyword is an addition to C++ 11 standard. So now I will talk about the motivation. Why is this important? I think it is a very, very important feature, especially for HPC. And so I will talk about the syntax, and then I will talk about the index because so I was thinking to present. So now this is the thing that Mauro already showed, but I will explain it again. So I think it doesn't hurt.
Well, you will explain for the first time.
Okay. And then I will present two examples, two reusable design that hopefully you can exploit maybe in your job. And there will be some exercises in this part for each of them. So one is implementing some expression template library, some like domain-specific language, and the other one is for dealing to multidimensional arrays indexing. So I think everyone already has the material. So I think it. So if you go to the folder code Constexpr, you can run the snippets that I will show while I'm talking. You can try them out, and I will sometimes go to the shell to execute some of them, and so everything is in this folder, and the exercises are in this exercises Constexpr. So if I would like this to be interactive, so that when I talk, you can try it out. So first, the motivation. So let's say that we want to compute the sum of the n numbers, and let's say that we don't know that there's an analytic way to do that, to sum them with looping over all them, but we want to do that with recursion. So if and we want to do this compile time and at runtime. So in the pre-C++ 11 version, you would have to define to have two implementations, two separate implementations for those. The runtime recursion. So it's recursion. It's calling sum with the ID -1, and when the ID is 0, when the ID is 1, it just returns ID. So this is the standard way you would have the runtime recursion. And with compile time, you do exactly the same thing, but you have this template, this recursive template, which is instantiating a type with a different I, with I -1. And then you have to also implement the specialization for the case in which for stopping the recursion. Then you also have in the main, you will have to define two different interfaces for the two things. So this is a runtime. I pass in a runtime value, and then they compute the sum runtime, and I do a cout, or I do it at compile time. So with Constexpr keyword, this would be the code you write to do this. So just the runtime version with a Constexpr keyword in front of it, and you can use the same syntax for compile time and runtime computation. Now, so the syntax is the first motivation. So the reducing the code, the size of the code. Then you can also have complicated types at compile time. So complicated values at compile time. With C++ 03, you can have a static const, which is you can use in a template parameters. You can only have integers or booleans, or you cannot have a double. And you can have a static const double, but this would not be a constant expression. So this adds something also to the allows to define complicated structure at compile time. Then the compilation time. So now I wanted to show you an example. So here I have a shell. So let's see. Example 0. So here I have the code which I was showing before. So we have the Constexpr version and the template recursion. So we want to measure the compilation, how much time it's taken by compiling both of them. So we first try with the template recursion. So we can time it. Example 00. So this takes 0.2 seconds. Now, if we compile, sorry?
You can compile.
Yeah. I have to use, because I have to use these flags. So it takes 1.7 seconds. So what if I now comment this out? I uncomment this. So this is the Constexpr version. So 0.3 seconds. So there's a big advantage in using Constexpr versus template recursion. Also the compilation time, and that's probably because you don't have to instantiate types. Constexpr has nothing to do with types, while the template recursion instantiates types with a different index every time. So now you can see another thing which is useful to see is the compiler explorer. Of course, you cannot pass this in your browser, but you can see it in the example. In the example 00, here's the same link. So you can pass this link in the browser, and you will get the link to the compiler explorer, which I have it here. So you have these Constexpr recursive function, and you see that this gets compiled a single instruction. So it's like the factorial example that Mauro was showing. Is executed at compile time, and it returns directly the result. So, but what if we change the compiler? And now this is with GCC 6.2. Let's say Clang 3.9, so the last version of Clang. So what happens? Here you see that there's a jump in the main. There's this function which has inside a function call. So there's a recursive function call. So this really has, this is not anymore one single instruction, and so it means that the compiler can choose whether to treat this at compile time or not. So now you may think, okay, Constexpr is like the inline. I say to the compiler, then he does what he wants. It's not exactly like that. So it's true that if it's not expression, this sum2, then it's up to the compiler to treat it as to evaluate it at compile time or runtime. But you can force the compiler to do it at compile time by instantiating a Constexpr variable. So this Constexpr must be a constant expression, and so this call of sum2 is used to initialize a constant expression. So the compiler is forced to do it at compile time. You see now also Clang only compiles this with a single instruction. So now, what about so we saw an example of Constexpr. Now the definition of a constant expression is an expression which is evaluated at compile time, but the meaning of the Constexpr keyword is not the same. So on a function return type, it means that it may or may not return a constant expression, depending on whether if it's used inside a constant expression or not. To initialize a constant expression, and it must return a constant expression. Otherwise, it might not. On a variable instance, it means that the instance is a constant expression. So, and when a constant expression function is used in an expression, it must return a constant expression. So this is the rule. Then the constraints for Constexpr function, you cannot put Constexpr on any type of functions and expect that you get a constant expression back. It must not contain a local. So this thing were very strict in C++ 11, and it got relaxed with C++ 14. So in C++ 11, you could not have local variables, you could not have if statements. You had to have a single return statement. These things, from C++ 14 on, they have been relaxed. So there's not this constraint anymore. The thing which still holds is that the arguments of the function must be literal. So a literal, there's a definition in CPP reference of what the literal type is. So it's very long to put in a slide, but basically, whatever you can instantiate at compile time as a constant expression is a literal type. So integers or aggregates or PODs are literal types, or we will see objects which have a Constexpr constructor are also literal types. So the arguments of a Constexpr function must be a literal type. So an example of non-literal type is a string. Standard string is literal type because it's allocating things on the heap, and it doesn't have Constexpr constructor. So cannot contain static variables, cannot be virtual, and some other details. So you can instantiate your own type as a constant expression, and this is something new that you could no way to do that in C++ 03. So in order to do that, your class must have a Constexpr constructor, and the Constexpr constructor must satisfy all the requirements, all the constraints of the Constexpr function. The class, if it's deriving from some objects or have some data members, all the base objects and data members must be literal types, must be Constexpr constructible. And so this is some mistake that the first time you use Constexpr you might fall in. You might try to put Constexpr in the function arguments. So the function arguments cannot be Constexpr. So the Constexpr is not. It doesn't go inside the type. It doesn't have anything to do with the type. You can have two things of the same type. One is Constexpr, the other not, and they are indistinguishable only from the type. So the compiler treats the arguments as constant expressions when the function is used inside a constant expression, for instance, to initialize a constant expression or inside a static assert. Otherwise, it's up to the compiler. And also the data member of a class, you cannot put Constexpr on a type of a data member of a class. This data member will be a constant expression if the instance of the class is a constant expression. So, syntax. So, what would you say about this function? Is this constant expression? So, is this valid? Can I put Constexpr here? Who would say that I can put a Constexpr here? So, this is a F1. It's getting a standard vector, and it's returning its size. I define the standard vector. So who says that it can be Constexpr? Who says it cannot? Okay, you're right, it cannot. You also say someone wants to explain me why? Yeah, good. Yeah, exactly. So a vector is not a literal. It allocates things on the heap. So doesn't have a Constexpr constructor. Now, what about these? Now I get a tuple as an argument, and then I return std get of the second element of the tuple. So who says that this is valid in C++11? Who says it's not valid? Okay, everyone gets it right. So this is valid because tuple is a literal type. So you can construct, it has construct, and std get is a Constexpr function. So you can do that. And
T is not the type we have.
this type, if this type, oh, sorry. So the question was, if this type is not a literal?
No, the capital template T that you pass, some of the types are not literals.
Yeah, in this case, it's not a literal type. So it's not, you cannot have it Constexpr if it's if the T is not, if the T, let's say that one of those is a standard string. Yeah. So here you could put Constexpr auto, and it would work, and it would be at compile time. Now, what about this example? So in this example, I pass a literal type, a std tuple. I create a local variable, which is a Boolean. I have an if statement inside the function, and two return points. So this case, compile with C++14. So all these things are illegal in a Constexpr function in C++11, but in C++14 you can have these at inside. Yeah.
Oh, there is the constraint. Does it work?
Yeah.
This has the constraint that the two return statement have the same
Yeah.
type. So it is a tuple of same types. Otherwise,
Yeah.
you get
Yeah,
a
yeah.
compiler error.
Yeah, exactly. Yeah. In this case, because because the return type has to be the same. So, to define your own class as a Constexpr, so you just have to label the Constexpr, your constructor as Constexpr, and it can contain the same things as the Constexpr function. So in C++14, local variables and if statements, you have to initialize this before the body of the constructor, but then you can also modify it inside the body, and all these can have it at compile time. So you can define Constexpr auto T, my Constext, my const, and passing a tuple. So all this works. By the way, you can try it in the 03.cpp. You can try to modify the code to break it and to see when it's not compiling anymore. So now, in the SCL, there are several things which are not cannot be constant expression, and some other which can be constant expression. Containers like vector or list or maps, they cannot be constant expression because they have an allocator which allocates the storage in the heap. So these things, you cannot have them at compile time. The string is the same function, and normally the algorithms and iterators, they're not, you cannot call them at not labeled Constexpr. Initializer list is not Constexpr. It is since C++14, and C++11 lambdas will be Constexpr in C++17. What is already Constexpr constructible in the standard library is a standard pair, a standard tuple, as we have seen. Then the std array, there's a lot of people implementing crazy stuff with Constexpr. So like this Sprout library is practically implementing the STL algorithms constant expression. So it works that you can traverse with iterators and find and use algorithms at compile time. And there's several libraries in this spirit. So one thing which is worth noticing is the addition to the C++11 to the C++17. So now this is not working. So this one can be labeled as Constexpr, a regular function, and this would work. But if we define a lambda, we cannot define it as Constexpr, not yet. When this will be possible, it will open. It will be a great improvement because we could. So all we do now is functional programming using template metaprogramming. So to do things like compile time. So if we have, if we would be able to define a Constexpr lambda, then we could replace all this template metaprogramming code with regular functional programming compile time. It would probably look much easier. So, but it's not available yet. So the template recursion has a limit, which is depending on the compiler. So I think the compiler for GCC is 900. If you exceed this number, it gives an error. You can specify a flag to the compiler in order for it not to break when you have a larger value here. So this is the same flag that is in the example 00. And the same thing is for Constexpr recursion. So this is the same code for Constexpr recursion. You will have limit set to 512 for GCC. Then there's one corner case. So can you tell me if this is a valid? If this is a Constext? If I can put a Constexpr here. Is this valid? Will this give me a compiler error? Then I use it inside the static assert. Who thinks that this is valid? That this won't give me a compiler error? And who thinks that this will give me a compiler error? So this is very tricky. This gives a compiler error, but just because I'm using it inside a static assert. And so the reason is that this ID can be, when this ID is 1, is divide returns 0, and I have something divided by 0, which will throw an exception. So things which throw exceptions, they cannot. So the error you get for this is non-constant condition for static assertion, which is like you don't know where this comes from. You say, okay, then the compiler is just not. So you would really think that Constexpr is like inline. So the compiler does what he wants. I specified a perfectly valid. Yeah. Okay. So you specify something that should be Constexpr, and then you get such error.
So here it doesn't work not because of the division, because the division becomes division by 0 at some point. So it's not because something can throw an exception that it will be not Constexpr. It's because during the evaluation it throws an exception, and at compile time you cannot do anything about it.
Yeah. So you can try. We can open the example 4. So if I have example 4. So this is the example which is not compiling. If I put here 1 instead of a 0, and I compile G++. So this compiles. If I put 0, it gives me the error. Non-constant condition is for static assertion. This is very tricky. You might have, this is a very simple example, you can spot it, but you might have very complicated stuff inside, and just find this error and wonder why it's not a constant expression. So it is probably because it's throwing an exception somewhere. So expressions with undefined results or throwing exceptions are not constant expression.
Is there any particular reason why the error message doesn't say?
Well, actually, it says something. It's got pretty good because it says this. So in this case, it's pretty obvious the error, but it might be obscure if the case was not very very simple. So it tells you that this is not a constant expression, so it cannot be more explicit than that. But for complicated stuff, it's probably difficult to understand. So how would you check if something is a constant expression? So this is kind of a trick, because the Constexpr keyword is not in the type. The type of a Constexpr thing is exactly the same as the type of a non-Constexpr thing. So what if you want to branch at compile time for Constexpr, non-Constexpr? So let's say that you have this struct, which has Constexpr constructor, Constexpr get, and you want to separate the two cases. So now we have one which is a constant expression and one which is not. So what you can do is you use the no-except keyword. So if you call no-except of a function get, which you didn't declare as no-except, you can also declare a function as no-except if it's not throwing exceptions. And so if it's not declared no-except, then you can distinguish these two cases, because a constant expression is no-except. So it cannot throw exceptions if it's a constant expression. So in this case, you would have a Boolean which checks if T1 is with the return type of no-except of T1 get. So this is evaluated at compile time, and this also checks if T2 is a no-except, and you will get true and false depending on the whether if the instance is a Constexpr or not. So this is a trick. You don't have it in the type, but you can still get it somehow. There's other tricks to do that, which is FINA. But these are really complicated. And look it up online, and it's if you want to complicate your code, use macros and everywhere, then go ahead. But I would not suggest it. Or sure that your things are Constexpr, just use a static assert and issue an error where they're not constant expression. So this is a good practice. So now this slide is because it doesn't have anything to do with constant expression. It's just because I will use it in one of the examples. So, and this is what Mauro already was showing in the stencil example. So if you have, if you want to, so we know how to transform a tuple. You just do make tuple, put the pack inside, and this works. So now, what if you have a tuple and you want to you have an API which accepts a variadic pack? How do you transform the tuple into the variadic pack? So let's say to be practical, that I want to create a vector, a standard vector where the size of each element with the size element of the tuple. So this is 8 is the size of the double, 1 of the char, 1 of a char, and so on. So you want to implement to have this thing implemented. So size of the first element, size of the second, and so on. So to do this, as Mauro showed, you can use the std integer sequence. So if you don't believe that this is a good way, you can try out. You can try to think of another solution, but you will realize that this is not trivial. So you need another pack. You have the pack of the arguments, but you need a pack of integers from 0 to n, to the size of the tuple. And this pack you have to generate somehow. So the way you can do that is that you create a helper function which is templated with a sequence, and you pass this as an argument, std integer sequence with the pack. And then here is the usual pack expansion. So you want to expand to this, so you call size of get id tuple, and you expand in the outside the size of. So to call this, you just create vector tuple and make integer sequence of dimension 5. So this means that you only have to specify the dimensions here. This actually is a hard-coded 5 because it didn't have space to put size of tuple, but this should be the size of the tuple. So you don't need to specify all the sequence, so 0, 1, 2, and so on. This gets automatically done here inside. So this is a way somehow to zip an integer, to attach an integer to each element of a tuple. I attach 0 to the first element, 1 to the second element, so on. So, so now, wanted to show you an example. So this is an example of defining a language which defines an algebra. So it's a ring algebraic structure which has two operations, a times and a plus. This is also an example of generic programming because this the things. So anyone has any questions so far? Something which was not clear, or?
I have a question about the no accept trick that you did before. Yeah. Could you maybe roll back quickly? So what happens if I qualify the get function with no accept?
Yeah, this wouldn't work anymore.
Ah, okay.
If you have do return, you cannot distinguish them anymore.
Yeah.
In that case, that's the thing. So if you use this with something that you didn't code yourself, then it might be declared as no accept. So it wouldn't work. If you define it, then you have the control. You can put no accept or not. So you can wrap a call inside something, and I mean there's ways to get around that. But yeah, this is because it's a trick. You're not supposed to do it. Okay, so we want to define a language for expressing algebraic expression, and our variables, which should be called x, they can be everything. So for this reason, it's an example of generic programming. The algebra of functions, an algebra of series, an algebra of matrix, whatever, and with the same code. So we want this code to be generic enough to support all of these things. So we want to be able to lazily evaluate the expression, so to define compile time and to evaluate it either at runtime or compile time, depending on the argument that we pass. So if the arguments are compile time arguments, we want this evaluation to happen at compile time. If they're runtime arguments, no, with the same code. And we want to we want to be able to define every combination of these operators. Then the second part of the exercise will be defining a differentiation rule for that. So we choose this as grammar, so we want to express this function with this syntax. So plus, sorry, the minus is not in the grammar, so here is a plus. I didn't put the minus in there. So Now I will show you it in an example. I suggest you just open the file in your folder. So it's in ET. So you can open the Constexpr main. Constexpr main. This is a very simple main. So we can comment out this because we don't have the grammar anymore. We don't yet have the grammar yet. We start defining a placeholder, right? Which is like a proxy for our variable. So this placeholder has a generic operator which takes an argument and returns it. But then we define a global variable which is called x, and will be our variable. So it is. You can find it in p.cpp. So the name of the files is always here on top. So you can open the file and find the code. So we can just copy it here. So now we can already express. So we can already write this. We can write an expression which is equal to x and evaluate it. Evaluate it in some point. So we can try to compile this. Constexpr main.cpp. This works. So maybe I just open. So out it prints 5. So this is a very simple language. So it only implements the identity operation. But it works as compiled. We can instantiate this at compile time. We can define it at compile time, evaluate it at runtime. We can also evaluate it at compile time. If I Constexpr x5. So if I have these, it's also compiling. So I can evaluate it at compile time and find it, evaluating lazily, and define it both at compile time. So now, to make it more interesting, we want to define some like like the plus operation. So for the plus operation, we want to define, we have two template arguments, one for the left side and one for the right side of the plus operator. And we want the evaluation, which is this operator parenthesis, to evaluate the left side and the right side at the point t of this generic type. So this can be whatever the generic type you choose. It only needs to implement an overload operator, and it can be whatever. And you return T1 in T and T plus, T2 in T. And then you have to write also the overload of the plus operator. So the plus operator will, for two generic arguments, T1 and T2, we return an instance of the expression plus. Not any, now I'm returning everything by copy. I'm not using any namespace. I'm not using any protection for this thing. In the real life, you have to do all these things because otherwise it's dangerous code. So now I add the plus to my first to my file. Now I can, let's see if it works. So I can add a plus to my expression. So try to compile this and to run it. You see? Okay, okay, now it is my mistake. I should have called expr here. So in the evaluation, so here I defined my expression and here I evaluate it. So now returns 10. So we already have like one operation in our grammar with very few lines of code. See, this is the old code that you need. So now we want to add our other operation. So we do exactly the same thing. So almost the same code. We just replace the plus here with the times. The operator. We overload the operator times instead of the operator plus. So exactly the same reasoning behind. So times.cpp, I copy this, I put it here. You can try to do the same. You know, if you want to try out different expressions to show that I did there's some bug in the examples. So now. Let's try to, okay, well, let's modify our expression with the time. So this gives 630, which hopefully is correct. I can try to, it's correct? Okay, now it's easier to see that it's correct. Okay, so we implemented our grammar with our ring algebra. The important thing is that here x can be numbers, can be also not numbers. I can put here instead of a double, I can put I don't know a char. It will work somehow. So it just doesn't make sense because you do operations with chars. But then you could have there your type and if you overload the plus and times operation, you can implement your algebra. So you can implement like matrix algebra or series function algebra. It's very useful because you have only one code and it's very short. So this is also an example of generic programming. Now comes so we can write our main function. It was 30 lines of code, about more or less. So now the difficult part comes in. We want to implement the derivative. So to implement the derivative, we use the chain rule. So the derivative of composed functions, and we can implement that in a recursive way, very easily. So we just have to define the derivative for all the expressions that we have. An expression which is the identity. So the derivative of the identity is 1. Then the derivative of plus operator is the derivative of the sum of the two derivatives, and the derivative of the times is the derivative of one times the other plus the plus one times the derivative of the other. So we start, and the derivative of the rest of the other things we put it to 0. So now we have to make an assumption. Well, we don't have to. We make an assumption that we are working with numbers, so we cannot work with matrices or other esoteric things anymore. But we could be more general. It's just for the sake of this course. You could implement also 0 and 1 types. 0, like two other extra expressions, which implement the 0 and the 1 in your algebra.
Yeah, I guess if you return there t curly empty curly braces, it will return the default constructed.
Yeah,
T,
for instance.
And you have to be sure that that is the null element of your algebra.
Yeah. And then you have to do also for the 1.
Yeah.
And but in this case, so for this time on, we work with numbers or with things which can be casted to numbers. So we define expression derivative. This is the primary template which returns 0. We create this operator d, which takes a generic argument. Why am I not using the and returns this expression, which is x derivative of t. Then we will have to specialize for all the other cases. So now let's add this. Is in d.cpp. So I introduce it here. Now I can call the D of one of those. Let's say I just call the D of X. So now, okay, evaluated is something which is not. It returns 0 because we only implemented the primary template. The primary template it returns 0. So everything we pass to the D returns 0 now. So for this reason, we have to specialize. Specialize first for our variable. So if I pass X to the expression derivative, I want it to return 1. So adding this to the code. Now I have my derivative of X, and I expect this to return a 1. And it works, so this returns a 1. So I have the specialization for the placeholder Now I write the specialization for the plus operator. So I want to implement this rule. So what T1 and T2, I have T2, I pass, I declare this type. So the type is the type which is returned by D of T1 plus D of T2. And I just call and just evaluate this type into T. So D plus okay, now I have to put something inside. So this should return 2. It returns 2. So here you can compose also the things. Well, I can have X plus these. We have 7 plus 2. Okay, this works. So we do the same thing for the task. Anyone has any questions? So it's someone have some doubts? Or okay, then I go on with the times. So the times is the same strategy. So you want to implement this rule. You do the decal type of exactly this expression. So T1 plus times T2 plus derivative of T1 times T2. And I evaluate this value T in the point T. So I add this part. So now I have to add times to the option. No. Yeah, here. So let's put the time here. So I obtain 14, which is 7 times 2. So it's the derivative 2 squared is 2x.
7 times 1 plus 1 times 7.
Yeah. And now, so now I have the derivative of all the operators. There's still something missing, which is the derivative of the derivative, which is the double derivative operator. This is more tricky. So the derivative of the derivative of the derivative, I first have to express the derivative of T1. So I only have one argument T1 this time. And I first have to express the derivative of T1 in terms of plus and minus, which is what this thing does. And then I have to wrap it around another expression derivative. So then I evaluate this in the point t, and this should provide me for the full syntax, so that I can so now I can try with a double derivative. This should return 2. And it returns 2. So now you can try to put, I don't know, to put any combination of these things inside and see if it works. Try to break it. It should work. I don't know what, but I'm pretty sure it's correct. you can try it. So now we have our expression, a very complicated expression, which is defined here as a constant. Then it can be evaluated at runtime, or can be like this can be a runtime value, this 7, or it can be evaluated at compile time value. So this is an example that is an example of generic programming, and the use for the use of Constexpr that might be of general purpose, so useful for several domains. So now it's so this is what I already showed. So the exercise now would be to count at compile time the number of sums and multiplications implementing this interface. So I want to know that this expression, and I want to call the dots, and I want this to return the total sums that are contained into these expressions. And the same for the multiplication. And I want here, I don't use this, I don't use the fact that this must be Constexpr, but I want these two numbers to be available at compile time. So I want to be able to put this inside a static assert. So I think how much time can we leave for an exercise? I think it's better to do this exercise and then continue with the next example.
I think 45 seconds. Well, you have 8 minutes until lunchtime. So.
Okay, so it's until lunchtime.
That sum ops is not only for the D operator, right?
It's for all the expressions.
It's for any expression.
It's for any expression must have this interface.
It's actually easier.
So you have the examples in the exercise folder, exercise Constexpr ET. I can show it here. Exercise Constexpr. So this one, count operations. Here it's already implemented what you saw, and you have to implement these two lines.